Hello everyone, welcome to Hydrology Hub. Why does HEC-RAS ask us to enter the river slope when we choose the downstream boundary condition as normal depth? Many engineers simply enter a value without understanding its physical meaning. However, if the slope is selected incorrectly, the computed water surface profile and flood inundation results may also become inaccurate. Today, we will understand the hydraulic theory, the governing equations, practical examples, and engineering guidelines behind this important concept. So, let's begin. Before discussing river slope, we must first understand the purpose of a downstream boundary condition. HEC-RAS computes water surface profile by solving hydraulic equations from one cross section to another. However, before these calculation can begin, the software must know the hydraulic condition at one end of the river. For subcritical flow, the downstream condition controls the upstream water surface profile. This downstream information is called the boundary condition. HEC-RAS provides several options, including known water surface elevation, rating curve, stage hydrograph, and normal depth. Among these, normal depth is probably the most commonly used option when downstream water level observations are unavailable. Now, the next question naturally arises: what exactly is normal depth? Normal depth is the depth of water that exists when the flow becomes uniform. Uniform flow means that the discharge, velocity, and water depth remains essentially constant along the channel. Under these conditions, gravity pulls the water downstream, while friction offered by the channel bed resists the flow. When these two forces balances each other, the flow becomes uniform. Mathematically, the friction slope, the water surface slope, and the channel bed slopes become approximately equal. This assumption forms the entire basis of the normal depth boundary condition used in HEC-RAS. But how does HEC-RAS calculate this depth? For that, it relies on one of the most famous equation in open channel hydraulics, that is Manning's equation. Let's now look at the governing equation. Manning equation is Q is equal to 1 by n A r to the power 2 by 3 s to the power half, where Q is the discharge, A is the flow area, R is the hydraulic radius, N is the Manning's roughness coefficient, and S is the energy slope. Notice something very important. The slope appears under the square root. This means that the slope directly influences the carrying capacity of the river. Without knowing the slope, HEC-RAS cannot determine the flow velocity of, or the corresponding water depth. That is precisely why it asks us to enter the river slope when we select normal depth. To understand this physically, imagine two rivers carrying exactly the same discharge. The first river is very steep, the second river is almost flat. Which river will have deeper water? The flatter river. Why? Because the flatter river has lower velocity. To carry the same discharge, it requires a large flow area, which means a greater flow depth. On the other hand, a steeper river allows water to flow faster. Therefore, the required flow area decreases and the normal depth becomes smaller. This simple physical explanation tells us why river slope is such an important parameter in hydraulic computations. So let us verify this mathematically with a numerical example. Consider a rectangular channel carrying discharge of 500 cubic. The channel width is 50 meter. Manning's roughness coefficient is 0.03 and the channel slope is 0.001. Since the water depth is unknown, HEC-RAS initially assumes a trial depth. Suppose we assume a depth of 4 meter. From this assumed depth, the software calculates the flow area, the wetted parameter, the hydraulic radius, and finally the discharge using Manning's equation. If the computed discharge is smaller than the required discharge, the assumed depth must be increased. If the computed discharge is larger, the assumed depth must be reduced. This process continues until the calculated discharge matches the specific discharge. Let us see the iterative process in more detail. HEC-RAS follows an iterative approach. It begins with an assumed water depth using Manning's equation. It computes the corresponding discharge. Then it compares the discharge with the specified discharge. If the two values are different, HEC-RAS adjusts the depth and repeats the calculation. This process continues automatically until the difference becomes exactly small. Finally, the depth at which the computed discharge equal to the specified discharge is called the normal depth. Fortunately, all these iterations are performed automatically by HEC-RAS, and the user only needs to provide the reverse slope. Now, let us examine how changing the slope changes the normal depth. This table clearly demonstrates the influence of reverse slope. When the slope is very flat, the normal depth becomes much larger. As the slope increases, the normal depth decreases steadily. The reason is simple. Steeper slope generates higher flow velocities. Higher velocities require less flow area. Consequently, the water depth becomes smaller. This is exactly what Manning's equation predicts. Therefore, even a small error in selecting reverse slope may influence the downstream boundary conditions and consequently the computed water surface profile. So, the obvious question becomes how should we select the reverse slope? Many beginners make the mistake of using the average slope of the entire river. This is generally not recommended. Instead, the slope should represent the downstream reach immediately upstream of the boundary. For example, suppose the bed elevation changes from 120.5 meter to 118.9 meters over a distance of 1600 meters, then the slope is calculated simply as the difference in elevation divided by the channel length, which gives a value of 0.001. This representative downstream slope is entered in the normal depth boundary conditions. Using the correct reach is extremely important for obtaining reliable results. Now, let's see how HEC-RAS exactly performs these calculations iteratively. Internally, HEC-RAS follows a logical sequence. First, it reads the discharge, the channel geometry, Manning's roughness, and the river slope. Next, it assumes an initial water depth. Using this depth, it computes the flow area, hydraulic radius, and discharge. These the computed discharge is then compared with the specified discharge. If they differ, the depth is adjusted and the entire calculation is repeated. Once the computed discharge matches the specified discharge within a very small tolerance, HEC-RAS accept the depth as the normal depth. This iterative procedure makes the normal depth computation both accurate and efficient. Now, let's discuss some practical recommendations based on engineering experiences. First, always extend your computational domain sufficiently downstream. This minimizes the influence of the assumed boundary conditions on the steady area. Second, estimate the river slope using surveyed cross sections or a reliable high resolution DEM. Third, perform a sensitivity analysis. For example, repeat the simulation trying slopes value such as 0.0008, 0.01, and 0.0012 or something else. If the water levels remains nearly unchanged, your model is considered stable. Finally, whenever reliable downstream stage observation or a rating curve are available, use those boundary conditions instead of normal depth. Normal depth is most suitable when downstream water level data are unavailable. It is widely used for natural rivers, flood inundation studies, dam break simulations, and primarily hydraulic investigations. However, avoid using normal depth if the downstream water level is controlled by a reservoir or tidal effects or hydraulic structures such as barrage or bridges. In such situation, a known water surface elevation or a rating curve provides a much more realistic downstream boundary condition. Choosing the correct boundary condition is just as important as selecting the correct river slope. Let us quickly summarize it. Normal depth assumes uniform flow at the downstream end. Under uniform flow, the energy slope is assumed equal to the riverbed slope. HEC-RAS uses Manning's equation together with discharge, channel geometry, roughness, and river slope to compute the normal depth. Flatter river produces deeper normal depths, while steeper river produces shallow normal depth. Always use the representative downstream reach slope rather than the average slope of the entire river. And finally, perform sensitivity analysis to ensure reliable modeling results. I hope this lecture has helped you understand not only how to enter the river slope in the normal depth boundary condition, but also why it is required from a hydraulic perspective. Understanding the physics behind the software is far more valuable than simply learning which button to click. If you found this lecture useful, please support Hydrology Hub by liking this video, sharing it with your colleagues and students, and subscribing to the channel. Thank you very much for watching. Keep learning, keep modeling. This is Hydrology Hub.